So what is balance, or unbalance, I should say? Basically, we're talking about unbalanced results from when you have uneven mass distribution around the axis of rotation of some rotating component. So the center of mass and center of rotation, I should say, are not aligned, and it basically creates some centrifugal force that can act on your rotating system and cause this unwanted vibration level, even leads to high acoustic levels as well. So when we're talking about getting rid of that, we're talking about balancing the system. That's going to involve removing mass if possible, and sometimes there's causing this uneven distribution, or maybe adding mass at specific locations to counteract the centrifugal forces that are created by this uneven distribution. Let's look at some examples here. So we have these two shafts spinning, same speed. Which one do you think vibrates more? Hopefully it's very obvious to you. That would be this one, with this mass added randomly here to the side. So yeah, shaft 2, right? That would be that uneven mass distribution that we talked about. Just an example of maybe how it would go down in the real world if you did have a situation like that. It's important that we address unbalanced situations in our rotating systems, because it can lead to excessive vibration, which usually is linked to excessive noise. It could reduce the lifetime of your product. So instead of lasting 5 years, it's done in a year before it just fails. It could be a safety risk, and this can affect the efficiency as well. Hopefully you can see that. See how quickly that can happen. So it can be a big problem, obviously, and very expensive and dangerous if not addressed. Looking at another example, we have these two spinning shafts again. This time they're spinning at different speeds. They both have this mass added very randomly to create this uneven mass distribution. But this one's spinning at 600 RPM, this one's at 6,000 RPM. Which one vibrates more? What do you think? Well, you'd be right, 6,000 RPM if you said that, because imbalance force is proportional to the mass times the velocity. So it's very sensitive to speed, basically. I think this probably drives it home better. We have on this chart the centrifugal force here, and then we have shaft speed, and we have two different imbalances. And they're usually given in units of like grams, centimeters, or ounce, inches, something like that. But two things hopefully are very evident. Number one, we can see that as you doubled the speed from 2,000 to 4,000, you actually got 4 times the amount of centrifugal force generated. Whereas just when we have double the mass, it's only twice. I should say double the imbalance, excuse me. And that's related to these equations right here, where the imbalance is times the mass times the distance from the center of rotation, and the angular velocity times the unbalance gives us the centrifugal force that's generated from this imbalance. So imbalance forces increase exponentially with speed, we talked about. So how do we fix it, right? We already talked about all the bad things associated with how do we fix it. Well, one thing you could do, I guess, if you could add another mass on the side of that, that'd be great. It'd balance it out. Or if you could remove, as we talked about, the mass, that imbalanced mass, that would also fix the issue. Now, there's different types of imbalance. They kind of fall in the category of single plane or dual plane. So we have the static unbalance, and that's where the principal inertia axis is displaced parallel to the axis of rotation, which we can correct by balancing one plane in this situation. Or we could have a couple unbalance, where this principal inertia axis intersects the center line or the center of gravity of our rotating component, and we would have to balance in 2 planes with this type of situation of imbalance. And then there's dynamic imbalance, which I think is probably the more common in many times, and that's where that principal inertia axis, center line, they don't coincide or touch, but we have this type of situation as demonstrated in the illustration. Causes of imbalance, besides the masses that we're gluing on in our little pictures, you could have something that's non-symmetric. Maybe it was manufactured incorrectly, or damaged, or if it's, they have these really huge generators that have huge shafts. If they don't run them for a long time, sometimes they can deflect under their own weight. So anything, some non-symmetry in the rotating parts can cause imbalance. Off center, so it's like maybe an alignment issue sometimes with the shaft can create imbalance. Or you could have a lot of clearance, which can cause a lot of in-play and lead to imbalance. Or as we talked about very early on, right, you might be exciting the resonance, like a shaft bending resonance, depending on what speed you're operating at, right? Because we know RPM can be related to frequency, and bar or plate, they have natural frequencies. So if you're exciting the shaft at one of its natural frequencies, that can lead to some unwanted imbalance issues. Just wanted to show you the setup. Basically, you'd have your laptop with test lab installed. You need to be in Signature, and you would just go to an add-in for the balancing. Some of the data, though, that we need to input to the program, RPM, right? So in this case, we're just using some type of optical tacho signal. And you'll notice that this one's being split. So it's being split because one's going to go into the tacho channel on our front end. This is our SCADA XS, but maybe you got a SCADA Mobile, but you're going to split it, that tacho channel, and one would go into the tacho on the front end, and the other channel would go into one of the inputs on the front end, one of your digital analog channels for measuring phase. We also see that we have an accelerometer on here, and ideally what we'd like to do is measure the response, that imbalance, in the plane somewhere along the shaft, but you notice that that accelerometer is not mounted there, and good reason. It's really hard to do that. Basically, you can end up with a situation like this if you did try to measure along the shaft. Now, this is my attempt at a joke. They didn't actually try to put an accel on a rotating drive shaft of this truck. Rather, what happened was, I don't know if you can see this material here, according to the internet, this truck ran over a mattress and somehow it got wrapped around the drive shaft. So that's some unwanted mass, uneven distribution along that shaft that probably created some big frustration for the driver when this first happened. Nonetheless, because we can't normally measure right on that plane somewhere along that shaft, what we would do is we calculate the influence coefficient, right? And that relates the vibration response to imbalance at a point close to it, which could be like a bearing. In this situation, you can see that maybe we would place the accel here. And what we have to do is make a couple assumptions that all the response that we're measuring at this point is due to the imbalance, and that there's a linear relationship between the response and imbalance. But we calculate this influence coefficient to allow us to be able to relate the change in response at this point to change in imbalance on our system, so we're able to properly balance it. So these kind of the steps to measure imbalance and how to correct it. So the initial measurement, we're going to just calculate the imbalance in our system. Then we add a test mass, and that's going to be a known mass at a known position, location, angle. Then we measure the system with this test mass. Then we do a calculation where we can determine the correction mass and angle that we need. And then we would remove our test mass and add our correction mass, and then verify at that point how well we did at removing the imbalance in our system. At the end of the day, what we'd hope is that after we've balanced it, we can see a before and after at the speed that this was the speed that it was done, the balancing. But we can see a significant reduction after balancing our rotating component in the system.